Hello and welcome back for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. In this episode, we are going to talk about congruence of squares optimization. Instead of searching for a, a square minus n that is equal to square, we can look into a much weaker condition where a square is equal to square mod n. It can be translated into square minus square equals 0, and that means that C plus D is a divisor of n. It means that either C plus D is a factor of n, or it could be trivial, like n or 1. What we are going to do is to search those values. So let's start. And if you have questions or comments, please post them in the Facebook group. The source code is also available on GitHub. Let's go. First, I want to do a few fixes from few changes from last episode. Instead of looking into bit lengths of squares, let's change it to be a bit length of n, like that. And now it's 44. Is it? It's not breaking anything. Okay. So this is our last episode. Now let's start a new episode. Let's rename it to episode 1. Now let's do episode 2. Cool. So now we are going to look on n square at 1 or 2 numbers. Why I did the n square? So another quick optimization that we didn't spoke about last time. Instead of searching for random numbers, we can start with numbers that are closer to n square. And then when you're performing a power 2 on those numbers, then the chances of the mod to be a small number are greater, because this value can be between 0 to n, while random values are, well, they can also be between 0 to n, but the probability for them being higher is bigger. So let's do that. We are going to search for those numbers. Let's have a loop of i's forever, no stopping condition. And let's look on big integer value of I. So this is the numbers that we are checking. It's our A. Then we are making it part 2, and we are testing what will be the result mod n. We are saying that A add mod square, because I believe that mod is a square. That is maybe solution. It can also be equal to n, in which case we don't want it. And we also don't want solution equals to 1. If it's none of those above, then we got this log. Oh Yeah, maybe solution. And break. Remove the old code. Oh, I didn't check if it's indeed a square. So if font is square, okay, looks better. Let's try it. And we got a value that it's not even a square. Oh, yeah. So it can be a multiplier um, of n. And to compute the value, we need to execute the GCD function. The GCD will give us the greatest common divisor between n and C plus d. It's a very fast function. It runs in O log n time, so we can execute it multiple times during our loop. So let's do that. So it's a square, and saying that A may be a solution. GCD. Yeah. Also, it's nice that we have GCD as part of Java native API. Let's try it now. Yeah, that was very fast. So we can improve the difficulty. Let's say 50, or even 60. Oh yeah, 60 beats takes 3 seconds. So that's an impressive improvement. Awesome. So this summarizes congruence of squares. Another improvement that I want to talk about on top of congruence of squares, let's call it episode 2.1, is adding a k. So we've been looking into values square n plus a small value of k, right? Let's call it k. And what we are doing now is we will multiply n by k, and then we will add an even smaller value of I. The idea is that after k is equal to, for k1 and above, this value, it's going to be higher than square n. It will be between square n to n until it will reach 2n, this expression, and then the mod loop will repeat itself. But the difference between square n and for k equals 3, so until that expression will reach 3n, it will take at least square n times. Yeah, I don't really know the mathematical explanation to it. This is why I'm asking this question, as you can see. But let's try this optimization, and I hope I can show you that it indeed works better. All right, so let's take that item and say that we are multiplying n by k for doing the square. And then I also want to iterate over small value of I, just like we did with k before. So let's have another loop. Let's say n, and that is going to be here. Now I want to use it for the square results. So before doing the square, I want to add I. Sorry. After doing the square results, I want to add I. So I want to look at A plus I. So A equals A and I. And the rest should be the same. Something like that. Let's try. Last time it took us 3 seconds. Let's see now. Looks the same. Let's increase it to 100 maybe. The same. Okay. Let me hit the magic button to see what's wrong. Okay, so I forgot multiple things. I need to run episode 2.1. Been running the wrong thing earlier. And let's change that to return. So we will break that loop and not this one. I don't need to add the k value here. So it's just a square of this expression. Okay. I cannot reuse a. I need to put it into a variable square. So it's going to be that. Let's try it. So running episode 2. So episode 2 was 2.5 seconds. And now it's all right. It's half second. Oh, so that's an improvement. Now let's try to scale up. Let's go to 65. 2 seconds. 70. 4.5 seconds. So this is awesome. Now we can go to 70-bit, which is more meaningful improvement. If you have any questions, please ask me in the Facebook group or comment below. And the source code is available on the GitHub page. Next time we are going to talk about some testing. I want to test it better, all those results, because to be frank, it could be just a luck that this approach is faster. We need to test it on multiple instances to reassure that it's indeed the case. So this is what we're going to do in next episode, and then we will start seeing some really serious optimizations that will take us wide faster, forward. Thank you. See ya.